We are going to tell you about parallel universes and either convince you that they exist or convince you that they don't within the next hour. So before we kick off, I'd really like to just sort of spell out that there's two very different ways in which physicists think about parallel universes, so we don't sort of get confused from the beginning. One of them is called the many worlds interpretation of quantum mechanics. And it's the idea that the universe we see in front of us is constantly splitting many billions of times, every billionth of a second. The entire universe fractures, and every single possibility that can happen does happen in one universe. That we're just following a path through one of this infinitely bifurcating tree of different universes. The other way of thinking about parallel universes is what's called the multiverse, and it's the idea that the universe is just much bigger than what we see around us, and that there's different parts of the universe that have different laws of physics applying within it. So I think in this debate we're going to be touching on both these different ideas of parallel universes. We have three of the world's experts on the subject here. On my right is Professor Vaidman from Tel Aviv University. He's an expert in the foundations of quantum mechanics and quantum teleportation. To my right we have Professor John Ellis. John has been for many years the theoretical guru in CERN, the particle accelerator in Geneva. On my far left we have Dr. David Wallace. David teaches in Oxford University. He's got two PhDs. He has a PhD in physics and a PhD in velocity. He's Dr. David Wallace.
All physics which I studied was deterministic and local. And people were telling me that collapse, which is kind of the opposite of the many-word interpretation, tell us that every time we make a quantum measurement, there is a collapse. Collapse is random and non-local. And I was not ready to accept it. This was against all physics. This is not a clear picture. I'm a really strong believer in many-word interpretation. I really believe that all what exists is just a quantum wave. Everything is wave. I'm a wave. But a quantum wave of so many particles is kind of a complicated object. The paradox of quantum teleportation is that I can be moved, in principle, from one place to another without specifying all these complicated objects. What it has to be moved is much smaller number of numbers. So the essence of me is just all this small number of numbers. I had a bad feeling about it. It's hard to know if it's true because the real experiment is problematic. But I believe that very soon it will be recognized that this is the right interpretation of quantum mechanics.
So as a physicist, I believe that our job is to formulate laws that describe the way the universe works. And for me, the only interesting proposals are ones that are actually subject, in principle at least, to experimental test. And so the question I would have for the many worlds interpretation, or for the multiverse for that matter, is how the hell do you actually test these ideas? Give me a prediction which is going to be different from what some other theory might predict. So I admit that nobody understands quantum mechanics, except that. Anybody except that who claims that he understands quantum mechanics is a knave and a fool, right? And I agree that the measurement problem it's baffling. My practice is to stop worrying and get on with it, right? So as a practicing physicist, of course every once in a while I wake up and have a nightmare about the measurement problem, but I don't let that worry me. I just get on with my day job. So I'm interested to hear from there how one would actually test the many worlds interpretation.
So here's the problem. Quantum mechanics, which is the theory that underlies pretty much all of modern physics, certainly underlies all the amazing stuff at CERN, it says some kind of weird stuff about matter. It seems to be saying that electrons, say, can be here and here at the same time, or can be spinning this way and this way at the same time. But then the theory says, well, if I look at the electron, if I have a measurement device that's supposed to go beep if the electron is here and boop if the electron is here, then if the electron is here and here at the same time, then the measurement device goes beep and boop at the same time, which doesn't seem to be what measurement devices do. And if I've got a slightly less ethical measurement device, where if the electron is here, it kills a cat, and if the electron is here, it doesn't kill a cat, then the cat's alive and dead at the same time. And that doesn't seem to be the kind of thing cats are observed to do. So there's something kind of weird going on in the theory. So the theory which is on the one at the same time our best theory ever is also in some ways our least understandable theory.
Does anybody want to comment on?
I just want to say that David did my job. He answered you. Because you said that there is this measurement problem, which is kind of a small thing. I spent all my career looking on this measurement problem. And I'm looking on this simple quantum experiment when this measurement problem kicks me in the face. I have to do something with it. And what I say, just, there is no collapse. There is no collapse. You have to admit that there are many worlds. So you have to bring an experiment which will show that there is a collapse.
So just to be clear, we all agree that quantum mechanics is right. We all agree that it gives the right predictions for every single experiment that's been done. Lev and David both say that means there's an infinite number of universes out there, and you're putting the onus on John to disprove the infinite universe.
Infinite.
No, so if I could chip in. Now, I threw the gauntlet down first. Right? I asked Lev to give me some experimental result that is explicable only within the many worlds interpretation and not within the conventional interpretation. So I'm waiting for that.
The difference between conventional interpretation and many worlds is that sometimes quantum mechanics breaks down because collapse is against quantum mechanics. Quantum mechanics works. I don't see any reason why it will break down sometimes. Because to say that there are no parallel worlds, you have to admit that quantum Schrödinger equations sometimes break down. The Schrödinger equation which you use, you have to add something else. And there is no any good candidate for collapse theory.
I would still like to hear what is the empirical test that I could make.
You make interference experiment with these particles, and then you put a mirror for this molecule. Today we don't have this technology, but it's not unthinkable.
So you're saying that John has to prove there aren't infinite numbers of universes, but he's saying that you have to prove
because John has to introduce a new law in physics. He has to bring me evidence, not I.
David, we need a philosopher to help us.
Okay, so one of the things philosophers do when you ask them to help them out is they don't give you straight answers, they just draw fine distinctions. So I'm going to do that, I'm afraid. When we talk about quantum mechanics, we often talk about interpretations of quantum mechanics, and we talk sometimes about the conventional interpretation of quantum mechanics. And I think that term kind of disguises two different ways you might think. So one is that a magic thing happens in physics that gets called the collapse of the wave function. And that thing means that for sufficiently big or sufficiently complex or sufficiently conscious or no one's ever quite clear systems, somehow the Schrödinger equation stops working. Now that's in principle testable. The tests are very, very hard, but they can be done. So that's one sense we could mean of conventional interpretation. And in that sense, this is perfectly testable. But there's a different thing people sometimes mean by conventional interpretation, which is something like this, that we do quantum mechanics, sometimes people say we shall calculate, and what we regard the theory as being is a kind of gadget to give us the outcome of experimental predictions, rather than somehow a literal description of nature. And I think all three of us think that quantum mechanics in some relevant sense is supposed to be descriptive of reality.
So perhaps I should sort of nuance my point of view somewhat. So indeed, on a day-to-day basis, I just stop worrying and get on with it, or shut up and calculate, as Vaidman used to say. And I think that's, if you really want to make progress in terms of discovering the Higgs boson, you have to do that. On the other hand, I have tried my hand from time to time at trying to think how you could imagine that the wave function might collapse, how you could, in some sense, augment or improve your understanding of quantum mechanics. I think it's a very, very tough business. It's very difficult to come up with experimental tests that you could really do to show how this happens. And I hear about Lev's conduct an experiment, and it sounds like it'd be a great thing to do, but I wonder how far away we are from actually being able to do it. I think there's, at least to me, an incredible conceptual price to pay for this. Right? So let's be, I mean, we were talking earlier on about the multiverse. So string theorists are relatively modest. They say there's 10 to the 500 different possible parallel universes, and they're all sort of clicking or beeping away in parallel. Right? But what is Lev saying? Lev is saying that there's this sort of bifurcation that is taking place everywhere in the universe at every possible instant. I don't know whether that finishes up with more than 10 to the 500 universes. It certainly sounds like a whole shitload of universes to me.
But may I clarify? People say many word interpretation, some people attack the name, but from physics point of view, there is a single physical universe. Words are different stories inside this big quantum state. And the coherence help us to say that they really don't interfere with each other. And the number is not so big. I believe that finally the universe is finite, so that everything is, and the number of these different stories is finite.
How many?
It's still quite big, isn't it?
It's pretty big. Now,
But there's something I never understood about it, which is that the whole universe splits, and the observer splits, and the person who's talking to the observer, unfortunately, also splits. I don't feel that I split.
So what happens is there's one of you and there's two of you, and that's happening between steps of your ability to notice it. So at least if you're prepared to be really kind of mechanistic and reductionist about the nature of human consciousness, then there just isn't a problem here.
So I'm splitting, I'm just too slow to realize.
Much better to say otherwise, yeah.
This raises in my mind an interesting question. So I'm reading these days about quantum biology, that people feel that there are processes, for example, in photosynthesis, in bird navigation, where the process is intrinsically quantum mechanical. In other words, it doesn't, but there's no collapse going on. Right? So is this compatible with what you just said?
Yes, I think so. Those processes are happening quantum mechanically, and just like any other process, we understand them as unitary quantum mechanics. We don't bring in any external collapse unless we get it from some mechanism.
but may I just, you say that you feel that there is only one of you. Now,
If it's any consolation, I only see one of you too.
John agrees.
really, one of the hard work in many word interpretation is to find correspondence to our experience. It's really a serious problem what I mean. From now on there will be two I. I spent a really special section about the meaning of I in many word interpretation. So this is legitimate and the right question, but the answer is that conceptually I has to be localized only in one place.
So one of the bits of, I guess, sort of circumstantial evidence that people put forward is that there are various parameters in the laws of physics that seem to be very finely tuned to allow human life to exist. Maybe human life's a bit of an exaggeration, but there's something called dark energy in the universe which makes everything repel. If it was slightly bigger, galaxies wouldn't have formed, so there's no way life would have had anyway. And so, this seems to lead to genuine problems in science. How can you explain these coincidences that we see all around us? And having a multiverse is, at least to my perspective, slightly better than having God as an explanation.
Oh, God again. I agree that there is an issue here, okay, and there is the A word. We haven't heard the A word yet today, but maybe now is the final.
You go for it.
This is the so-called anthropic principle. So I regard this as being terrible. Right? It's totally anti-scientific. You're sort of basically given up on the idea of finding some scientific explanation or some sort of correlation between different observables. And so I really don't like that idea. And I don't like that particular way of motivating the the multiverse concept either. And I'm sorry I'm beginning to sound like a worn-out record here, but I would just like some sort of empirical test of any of these speculations. And if you can't give me an empirical test, then you're doing philosophy.
I'm a little bit puzzled. I would expect that physicists would like to have an equation which explains everything, and this is what quantum mechanics with many words does, because we have to add something to this equation to say that there are no other many words. I would expect that philosopher will attack me because say that many words is somewhat problematic. From physics point of view, we have an equation. This equation works extremely well, as you agree. Why don't you want to stick with it and you want to say that something wrong with it?
So to finish up, we have these sort of vague, speculative ideas, some will say speculative, some will say very solid ideas, that there are parallel universes. And of course there are real problems in physics, real experimental problems that we still need to solve. What's dark matter, what's dark energy, what's LHC going to discover next? Does this help at all? Do any of these speculations impact what we really should be doing as physicists, which is answering what's coming up in future experiments? Lev?
I think this is really very important. In the beginning of the century, when we had these real paradoxes, we had problems which are telling us that our theory is wrong. We had to change the theory. So I'm not sure that we have today a theory which runs into a paradox. There are some things which we don't have a theory from. If we'll have a real paradoxes, I will say, okay, we should change our equation. Change equation, the many words are gone. Today, I think the physics explain very well what we have, and things which doesn't explain, there is a lot of data which we just don't get.
So, what this written on my T-shirt describes about 4% of the universe. Okay, and in addition to what this describes, okay, there's the dark matter, which is another 25% or so, and then there's the dark energy, which is another 70% or so. So, there's a lot more that we particle physicists need to understand, a lot more that we need to do in order to unravel what's going on with the other 96% of the universe. So, we've got a couple of small details to figure out there.
David, last comments?
Let me just pick up on something John said about the kind of responsibility of physics here, because oddly enough, I agree with this, though. I think if the many worlds way of understanding quantum mechanics doesn't make sense, or it's somehow conceptually unacceptable in some sense, then we've got a big problem in physics, and I absolutely agree that the responsible thing to be doing in physics, in that case, is to be worrying away at it. In the sense, the many worlds framework, as I said, is quite conservative. It's kind of, it says the theory we have is fine. So of course, it might have problems with it, but we're not driven to those problems philosophically. So I very much respect the position that says this isn't okay conceptually, so we recognise we've got a big problem in physics, we should think about it. The position I've got less time for is the one that says, well, many worlds doesn't make sense, but we're just totally happy with quantum mechanics as it is, and we should just get on with things.
Okay, well, that about wraps it up. I guess we've covered parallel universes, string theory, free will, and death, which is not so bad. Could you please thank all three of us?
For more debates, talks, and interviews, subscribe today to the Institute of Art and Ideas at IAI TV.